Before the age of electromagnetic harmony, the world of physics was a realm divided by uncertainty and incomplete truths. The mid-19th century stood at the crossroads of discovery, where scientists wrestled with invisible forces they could neither see nor fully explain. Electricity sparked curiosity, but remained a mystery. Magnetism influenced metals and compasses, but seemed to belong to a different world entirely. Nature appeared to be governed by scattered laws that did not yet speak the same language. This was the chaotic world James Clerk Maxwell would one day inherit, a world that yearned for unity yet had no idea how close it was to finding it. The early decades of the 1800s were a time of wonder and confusion. The Industrial Revolution was transforming factories and societies, but the invisible powers behind electricity and magnetism were still beyond comprehension. When people saw static sparks or lightning, they called it electricity, but what exactly it was, no one knew. Benjamin Franklin had named positive and negative charges a century earlier, but his understanding was more philosophical than physical. The notion that electricity might move, flow, or even carry energy was still vague and uncertain. Meanwhile, magnetism had its own mysteries. A simple magnet could align iron filings in beautiful patterns, could guide sailors across vast oceans with the steady pull of the compass needle, and yet, the cause of that attraction remained completely invisible. Physicists of the time described magnetic poles and forces, but could not visualize what connected them. The link between electricity and magnetism had not yet been discovered, and so, science treated them as distant relatives rather than siblings born from the same cosmic law. This confusion ran deep, not only in theory, but in language. Each scientist had their own terms, their own interpretations. When Alessandro Volta invented his electric battery at the dawn of the 19th century, it provided a continuous source of current, something completely new, but no one could fully explain how or why it worked. Then came André Marie Ampère, who discovered that electric currents could exert forces on each other, just like magnets. Yet even he could not imagine the invisible fields that surrounded these currents. To the physicists of that era, forces acted instantaneously, with no medium or field between them. They believed in action at a distance, a phrase that captured their struggle to explain how one object could affect another across empty space. Michael Faraday, a man of little formal education but enormous intuition, changed that view. He imagined lines of force, threads of energy stretching through space, connecting every particle, every field, every atom. Faraday drew them, visualized them, even felt them as real, yet many of his peers dismissed his ideas as artistic rather than scientific. To them, fields were metaphors, not measurable realities. Mathematics ruled the halls of theoretical science, and Faraday's hand-drawn lines seemed far too simple to explain nature's complexity. But beneath his drawings lay a profound truth, one that would later become the very foundation of Maxwell's work. The world of physics at that time was like a grand orchestra without a conductor. Each branch, mechanics, heat, electricity, light, played its own tune, unaware that they were part of the same symphony. Isaac Newton had once unified the heavens and the earth under his laws of motion and gravity, but that was in the 17th century. Since then, the universe had revealed new forces, new phenomena that Newton's equations could not describe. Light, for instance, was still a battlefield of ideas. Was it made of particles, as Newton believed? Or was it a wave, as Thomas Young's double-slit experiment had suggested? Both camps presented convincing evidence, and neither could be fully dismissed. The debate between the wave and particle nature of light raged on, dividing even the greatest minds. This intellectual tension mirrored the state of science itself, a mixture of brilliant insight and frustrating incompleteness. The equations describing motion and gravity were elegant, but they did not account for electricity or magnetism. The laws of thermodynamics were emerging, describing heat and energy, yet no one knew how they fit with the invisible currents that powered telegraphs or shocked experimenters in their laboratories. The universe appeared fragmented, its laws scattered like unassembled pieces of a cosmic puzzle. As the 1830s unfolded, experiments became more daring. Hans Christian Øysted's discovery that an electric current could deflect a compass needle was nothing short of revolutionary. For the first time, electricity and magnetism were caught in a single act, bound by an invisible connection. This one experiment shattered centuries of separation and hinted that both phenomena were linked at their core. Scientists began to suspect that nature's invisible forces were not separate actors but parts of one greater story. Yet still, they could not write the script. Physicists began to realize that every discovery raised more questions than it answered. If electricity could create magnetism, could magnetism create electricity? Faraday would later show that it could, through his experiments on electromagnetic induction. By moving a magnet near a coil of wire, he generated electric current, proving that changing magnetic fields could indeed produce electricity. But again, the mechanism behind it remained mysterious. What was actually moving? What was waving? What was vibrating in that invisible void between the magnet and the coil? The concept of the electromagnetic field was still unborn, waiting for a mind that could weave it all together. Meanwhile, the rest of science was marching on, unaware of how deeply this coming revelation would reshape everything. Chemists were breaking down atoms into simpler elements, unaware that electric charges and forces would one day explain chemical bonding itself. Astronomers were mapping the heavens, not realizing that electromagnetic radiation would soon allow humanity to peer beyond the visible stars. In every field, progress was happening in isolation, disconnected by the lack of a unified understanding of nature's forces. Even the philosophical foundations of science were unstable. The idea of other dominated the imagination of physicists, a hypothetical invisible medium thought to fill all of space, carrying light waves much like air carries sound. The ether was everywhere and nowhere, a desperate attempt to explain how light could move through empty space. Scientists imagined it as a delicate, frictionless substance that permeated all matter, unseen but essential. Yet no one could detect it. No instrument could measure it. Still, it persisted in theory because it provided the illusion of explanation. In this world of partial truths, physics was like a map with vast blank regions labeled unknown. Great minds struggled to draw connections where none seemed obvious. They saw the effects of forces but not the essence of them. The electric spark, the magnetic field, the beam of light, all were real, observable, and measurable, yet their true nature remained hidden behind a curtain of mathematical mystery. The more scientists explored, the deeper the confusion grew. Then there was the problem of communication between theory and experiment. Experimentalists like Faraday observed phenomena intuitively, while mathematicians like Laplace and Poisson sought perfect equations to describe them. But the two groups spoke different scientific languages. One relied on observation, the other on abstraction. Their worlds rarely met, and when they did, they struggled to understand each other. The scientific community needed a translator, someone who could bridge the precision of mathematics with the intuition of experiment, who could turn Faraday's invisible lines into something measurable, predictable, and universal. That person would be James Clerk Maxwell. But before his arrival, the field was a landscape of chaos. By the mid-19th century, the electric telegraph was beginning to connect continents, signaling the dawn of global communication. Yet even as humanity harnessed the power of electricity for practical use, it still didn't fully understand the science behind it. Engineers could build machines that worked, but no one could explain why they did. It was as if civilization was using tools from a book whose pages were half written. Nature's deeper logic remained hidden in mathematical shadows. At universities across Europe, students studied separate subjects: mechanics, optics, magnetism, as if they belonged to different worlds. They memorized formulas without realizing those formulas were fragments of a greater truth. The unity of physics was not yet imagined. Every discovery seemed isolated, a beautiful island floating in an ocean of unknowns. Even the simplest question, "What is light?" was answered differently by each scientist, depending on which theory they followed. It was into this intellectual storm that Maxwell was born in 1831. The world he entered was scientifically rich but conceptually divided. The groundwork had been laid by giants, Newton, Faraday, arrested Ampère, but their work existed in fragments. Maxwell would later gather these fragments and forge them into a single, unified theory. But before his equations could change the world, the chaos of his time had to be understood for what it was: a necessary disorder, a fertile soil from which the seeds of modern physics would grow. The story of pre-Maxwellian physics is not one of failure but of searching. It was a journey through fog, where each experiment lit a candle of knowledge, but no one yet knew how to connect those lights into a constellation. Scientists had glimpsed parts of nature's face, but not the whole portrait. They spoke of forces, without understanding fields, of fluids, of electricity flowing through mysterious channels. Theories competed, experiments contradicted one another, and yet progress marched on blind but determined. Amid this confusion, an idea began to stir, a sense that perhaps all forces were connected, that nature might be governed by a deeper unity hidden beneath its diversity. It was only a whisper at first, present in Faraday's sketches, in Enristed's compass, in Ampere's experiments, but that whisper would grow into a voice, a chorus, and eventually into the grand harmony that Maxwell's equations would reveal. The first half of this story ends in that fragile moment, when physics, filled with mystery and contradiction, stood on the edge of transformation. The scattered pieces were all there: electricity that could move, magnetism that could shift, light that could travel as a wave. What was missing was the bridge between them, the understanding that they were all part of the same magnificent phenomenon. The stage was set, the instruments ready. All that remained was for a mind capable of hearing the hidden symphony to bring order from chaos. That mind was soon to emerge, and when it did, the universe would never look the same again. The middle of the 19th century was an age trembling with the energy of transformation. Steam engines roared through cities, iron rails stitched nations together, and yet the very nature of the forces driving this mechanical world remained uncertain. To scientists, electricity and magnetism were curiosities, powerful, unpredictable, and somehow intertwined with light itself. Every laboratory in Europe hummed with experiments that hinted at a grand secret, but no one could yet read the message written in sparks and magnetized needles. Faraday's discovery of electromagnetic induction had ignited imaginations across the scientific world. When he moved a magnet near a coil and watched the galvanometer's needle twitch, he had opened a doorway to an invisible realm. But though he had seen the effects, he could not describe them mathematically. To him, lines of force were real entities, threads that filled space and carried energy. But in the language of his time, that idea was almost heresy. Theories were supposed to be built from equations, not intuition. Many dismissed his work as elegant speculation. The physics establishment wanted numbers, not drawings, and yet, beneath the skepticism, the cracks in old ideas were widening. Action at a distance. The ancient doctrine that forces could act instantly across space was starting to feel fragile. How could one charge affect another without anything between them? How could a magnet influence a needle on the other side of the table if the space between them was empty? The questions gnawed at the edges of Newton's majestic laws. The older generation defended the old framework, but younger scientists sensed that something was missing. An unseen medium, a hidden field through which these forces traveled. This was the moment when the ether once again captured the imagination of physics. Scientists believed that light, electricity, and magnetism all moved through this invisible ocean. They imagined it as infinitely elastic yet without resistance, as if the universe were submerged in a ghostly substance that carried every vibration. Every new discovery was forced to fit inside this model, whether it truly belonged there or not. In trying to explain everything, the ether explained nothing. Yet without it, the world made even less sense. In laboratories from London to Paris, experimenters tried to tame the unknown. They wound copper coils by hand, built crude batteries, and watched sparks jump through the air with a mixture of awe and fear. Each spark seemed to whisper of a deeper truth, of an order yet undiscovered. Telegraph lines stretched across continents, making communication instantaneous for the first time in history, but the theory behind their operation remained cloudy. The invisible forces that transmitted human words along metal wires were still regarded as strange magic. Humanity could use them, but not yet understand them. Meanwhile, mathematics stood apart, cold and elegant. Mathematicians like Laplace and Poisson could describe gravitational and electrostatic forces with impeccable precision, but only under the assumption of stillness. No change, no motion, no wave. They described a world frozen in balance, not the restless world that Faraday saw in his laboratory. The difference was philosophical. Faraday believed in the flow of energy through space. The mathematicians believed only in forces between particles. Their equations were powerful but lifeless, confined to static conditions. The real world, filled with dynamic motion, induction, and oscillation, demanded a new language, one that could describe living fields rather than frozen numbers. Across Europe, the tension between these two visions of nature grew. Some scientists, like Wilhelm Weber in Germany, tried to bridge the gap by modifying Coulomb's laws to include velocity and acceleration, hinting at a dynamic relationship between charges. Others pursued the ether model, filling it with imaginary whirlpools and vortices to explain magnetism. These early theories were clumsy, beautiful failures, valiant attempts to impose order on chaos. They revealed the yearning for unity that had begun to burn within the scientific spirit. In this atmosphere of uncertainty, every discovery seemed to contradict the last. Light could behave like a wave in one experiment and like a stream of particles in another. The newly emerging field of thermodynamics showed that energy could transform from one form to another, yet no one knew how electromagnetic energy fit into that picture. Was the energy of a magnetic field the same as the energy of motion or heat? Could it be stored, transferred, converted? No one could say for sure. Even the units of measurement were inconsistent from one laboratory to another. The dream of a single coherent theory of nature seemed impossibly distant. And yet, the clues were there, scattered across the pages of scientific journals, lying quietly in the notebooks of men who never met one another. Faraday's drawings of field lines, Ampere's equations of current, or Rosted's compass deflection, all fragments of a greater mosaic waiting to be assembled. It was as though nature had written her secrets on separate pieces of parchment and scattered them across the world, challenging humanity to piece them together. But before that unity could emerge, physics had to confront its own limitations. The 1850s were a decade of reckoning. Experiments on light's polarization and interference confirmed that it behaved as a transverse wave, not a longitudinal one like sound. That suggested that whatever medium carried light must be capable of supporting sideways vibrations, a property that no known material possessed. The ether, once again, was invoked, endowed with magical qualities no matter could have. It was elastic but weightless, rigid but fluid. Each contradiction made the theory weaker, and yet it persisted because no alternative existed. In classrooms, professors taught equations that worked beautifully for electricity at rest, but collapsed the moment anything changed. They could calculate the force between two static charges, but not the energy stored in the space around them. They could predict the direction of current in a wire, but not the waves of disturbance that might ripple outward when the current began to flow. It was a science of fragments, useful for machines, useless for truth. Then came the rise of experimental ingenuity. In laboratories filled with copper glass and the smell of ozone, scientists began to measure the speed of signals, the induction of currents, and the patterns of magnetic fields. Each result was a window into the invisible. The more they measured, the clearer it became that electricity and magnetism were inseparable partners in a cosmic dance. When one changed, the other responded. Every flicker of current sent ripples of magnetism outward, and every moving magnetic field called electricity into existence. Nature was whispering a secret of symmetry that only a mathematician fluent in both languages could translate. James Clerk Maxwell was still a young man when he began to study Faraday's work. Where others saw vague sketches, he saw geometry. Where others dismissed intuition, he sensed deep structure. He realized that the lines of force Faraday imagined were not metaphors. They were real, measurable, and could be described by equations. But before Maxwell could give them form, he had to step into the battlefield of conflicting theories that defined his age. The scientific world he entered was still dominated by the shadows of Newton and the assumptions of absolute space. The concept of a field as something that existed independently in space was radical. To claim that empty space could store energy, transmit waves, and carry momentum was to challenge centuries of belief. Before Maxwell, the very idea of a self-sustaining electromagnetic wave was unthinkable. Light was either a vibration of the ether or a stream of particles, nothing more. Electricity and magnetism were curiosities of engineering, not of the cosmos. Even Faraday, whose imagination had come closest to the truth, lacked the mathematical training to turn his intuition into theory. The time was ripe for someone to merge the two cultures of science, the intuitive and the analytical, into one coherent vision. Looking back, it is remarkable how close the world stood to discovery and yet how far it felt. Every crucial observation had been made, every piece of the puzzle lay on the table. But without a unifying language, those pieces remained disjointed. Nature's song was playing, but humanity could hear only scattered notes. In the absence of synthesis, confusion reigned. This confusion extended beyond physics into philosophy and even theology. Many scholars saw electricity and magnetism as vital forces, manifestations of a divine energy animating matter. The line between science and mysticism blurred. Some believed that the ether was the seat of consciousness or the medium of the soul. In this sense, the chaos of pre-Maxwellian physics was not only scientific, it was cultural. The invisible world was both feared and worshipped. Lightning was God's weapon, magnetism a cosmic breath. Only with time and clarity would the universe reveal itself as governed by consistent, natural laws. The later 1850s and early 1860s would finally bring that transition, but in the years before, the uncertainty was profound. Even basic concepts such as charge, current, and potential were defined differently by different scientists. There was no standard system of units. One scientist's equations might look completely different from another's simply because they measured current in different ways. The world needed not only a theory but a framework, a structure capable of organizing both experiment and mathematics under one roof. In this chaotic landscape, imagination was as important as precision. Without imagination, the facts meant nothing. Without precision, imagination collapsed into fantasy. Faraday had provided the imagination, Ampère and others had provided the measurements. What was missing was a bridge between them. A mind capable of translating lines of force into symbols, of turning physical intuition into mathematical law. That bridge would soon appear, but before it did, the disorder of the old world had to reach its breaking point. By the time Maxwell began his studies at Cambridge, the stage was perfectly set. Generations of confusion had produced a mountain of experimental data and a maze of competing theories. The ether reigned supreme yet was visibly crumbling. The wave theory of light was accepted but incomplete. Electrical theory was useful but blind to magnetism. The great revolution was waiting, silent but inevitable. The history of science often shows that before clarity comes, confusion must peak, that the mind of humanity must first drown in questions before it learns how to breathe answers. And so, in the decade before Maxwell published his monumental work, physics existed in that twilight zone, half knowing, half lost. The world of science was like a vast sea churned by invisible currents, with islands of knowledge rising here and there, unconnected and mysterious. Each discovery seemed to beckon toward unity, yet the path was obscured by tradition and uncertainty. No one yet realized that the answer to all of it, the behavior of light, the structure of electricity and magnetism, even the propagation of energy through space, was already embedded in the mathematics waiting to be written down. That is the meaning of the chaotic age before Maxwell, not chaos as disorder, but chaos as potential. It was the moment just before dawn, when the world is dark but charged with the promise of light. Scientists had glimpsed the edges of a vast truth, and every failed theory, every mistaken assumption was part of the process by which that truth would emerge. The confusion was not a flaw, it was the necessary turbulence before the calm of understanding. When Maxwell finally appeared, he did not destroy the work of those before him, he completed it. He gave structure to Faraday's vision, order to Ampere's forces, meaning to the ether's confusion. But that harmony was only possible because of the disorder that came before. The chaos of 19th century physics was the fertile ground from which the unity of electromagnetism would rise. It was the age when nature spoke in riddles, and humanity, fumbling through sparks and magnets, began to decipher the language of the cosmos. And as the final decades of that century unfolded, when Maxwell's equations began to reveal their power, the world would finally understand that all those scattered discoveries, light, magnetism, electricity, were not separate notes, but chords of one symphony. The confusion before Maxwell was the overture, the cosmos after him was the song. In the heart of the 19th century, when science was still searching for unity among its many fragments, there emerged a quiet mind from the misty hills of Scotland, a mind that would see patterns in chaos and connections where others saw divisions. James Clerk Maxwell was not a man of spectacle or fame, he was a man of vision, one whose imagination stretched beyond the laboratory walls into the unseen world of fields, forces, and invisible waves. Where others saw equations, Maxwell saw harmony. Where others saw phenomena, he saw symphony. And in that vision, he began his life's most profound mission, to unite electricity and magnetism into one coherent truth. The world he inherited was divided. Electricity and magnetism were known to interact, but no one could explain their connection in full. Faraday had shown that a changing magnetic field could produce an electric current, and Rasted had demonstrated that an electric current could deflect a compass needle. These experiments whispered of a bond between the two, but the language to describe that bond was missing. The experimentalists had glimpsed a mysterious relationship, yet they could not capture it in the rigorous grammar of mathematics. The mathematicians, on the other hand, had the symbols but lacked the imagination to see the living forces beneath them. Maxwell stood between these worlds, fluent in both their languages. From an early age he possessed a rare gift, the ability to visualize physical reality in mathematical form. To him, equations were not abstract constructions, they were expressions of nature's poetry. He saw mathematics as a lens through which the invisible could become visible. As he once wrote, "The equations are not merely calculation, they are the very essence of the thing." And with that belief, he began to weave a tapestry that would forever alter the structure of physics. Maxwell's journey began with his fascination for Michael Faraday's experimental work. Faraday had filled notebooks with drawings of magnetic lines of force, curving, looping, bending through space, describing how magnets and electric currents interacted. But Faraday lacked the tools of calculus and vector analysis. He could describe the patterns but not quantify them. Many scholars dismissed his sketches as intuitive art rather than science. But when Maxwell studied Faraday's lines, he saw something deeper. He saw geometry, continuity, and potential for mathematical expression. He realized that those invisible lines could be written down, measured, and predicted. At Cambridge, where Maxwell refined his education, he was surrounded by the precision of Newtonian thought. Yet he sensed that Newton's universe, composed of solid particles and instantaneous forces, was no longer enough. Nature, as he saw it, was not made of isolated objects acting across empty voids but of fields, continuous fabrics that filled all of space. These fields could carry energy, vibrate, and interact. They were the true stage upon which the universe played its music. Maxwell's challenge was to prove it. His mind worked differently from his contemporaries. He approached problems visually, often sketching mental images before writing equations. He imagined electric and magnetic fields as systems of tension and pressure, like invisible fluids flowing through space. This was not merely metaphor. It was intuition translated into form. He saw electricity as a kind of displacement in this invisible medium, magnetism as its rotation or twist. Though later science would discard his mechanical analogies, they served their purpose. They helped Maxwell build a consistent mathematical model of how electricity and magnetism interacted through space and time. The 1850s were the beginning of his transformation from gifted theorist to revolutionary thinker. During these years, Maxwell began to develop the concept that would define his legacy, that electric and magnetic fields were not separate entities but deeply interwoven manifestations of the same phenomenon. When an electric field changed, it gave birth to a magnetic field. When a magnetic field changed, it produced an electric one. The two were inseparable, like rhythm and melody in a single song. The realization did not come all at once. It emerged through years of exploration and refinement. He began with equations describing electricity and magnetism as known from the experiments of Coulomb, Ampère, and Faraday. Each equation worked well on its own, but failed to describe the complete picture. It was as though scientists had drawn the outlines of a painting, but left the center blank. Maxwell's genius lay in recognizing what was missing, and filling that empty space with an insight that would change everything. He noticed something strange in Faraday's law of induction. When magnetic fields changed, they created electric currents. But what happened when no conducting wire was present? Could a changing magnetic field create an electric field, even in empty space? The mathematics suggested yes, but the existing laws could not account for it. Likewise, when an electric current moved, it created a magnetic field, but if the current stopped, the theory predicted that the magnetic field would vanish instantly. Maxwell knew that could not be right. Nature did not allow such abrupt discontinuities. There had to be a mechanism, a continuity, that carried the transition smoothly through space. That insight led Maxwell to introduce one of the most profound ideas in the history of physics, the concept of displacement current. It was a bold addition, an invisible form of current that existed not in wires or matter, but in the fabric of the field itself. This term allowed the equations to maintain balance even when no actual charge was flowing. In doing so, Maxwell closed a gap that had puzzled physicists for decades. More importantly, the addition revealed something astonishing: the possibility that electromagnetic fields could sustain themselves and propagate through space like waves. It was as if the universe itself could sing. The electric field generated the magnetic field regenerated the electric, and together they could travel endlessly through space. The mathematics whispered a secret. The speed of these self-propagating waves was the same as the measured speed of light. And from that whisper, Maxwell heard the voice of revelation. Light was not a separate phenomenon at all. It was an electromagnetic wave, a vibration in the same field that carried electricity and magnetism. This discovery was not merely a scientific step, it was a philosophical leap. For centuries, light had been a mystery that divided science into factions: particles or waves, corpuscles or vibrations. Now, through Maxwell's vision, light found its home within the electromagnetic framework. The barrier between optics and electromagnetism dissolved, and with it, the boundary between the known and the unseen. Light, electricity, magnetism, all were unified as expressions of one grand reality. The power of Maxwell's equations went beyond description. They revealed a structure of the universe more profound than any before. They suggested that space was not empty, but alive with energy, capable of carrying waves across vast cosmic distances. They foretold the existence of all electromagnetic radiation, radio waves, microwaves, X-rays, long before technology could detect them. It was as if Maxwell had opened a door to an invisible spectrum of the cosmos. Yet when he first published his ideas in 1865, the world was not ready to understand them. His equations were long, complex, and filled with terms that defied the mechanical intuition of the time. Many physicists, comfortable with tangible models, could not grasp the beauty of the mathematics. They still clung to the ether, still believed in forces acting through invisible substances. Maxwell's field theory was too abstract, too far ahead of its age. Even so, he continued to refine it, confident that truth would one day outshine skepticism. In his vision, electricity and magnetism were not merely forces. They were the very language of nature. They were the medium through which energy traveled, the means by which light crossed the void, the hidden pulse of the cosmos. Maxwell imagined the universe as a vast network of interconnected fields, each vibrating, resonating, interacting across infinite space. Every atom, every planet, every beam of light was part of this grand electromagnetic web. To truly grasp the depth of Maxwell's vision, one must imagine the world before it. Scientists could see light but could not explain its nature. They could create electric sparks, but could not link them to radiation. They could use magnets, but could not tell where their power came from. Maxwell looked into this confusion and saw a single pattern underlying all. He realized that the universe was simpler than it seemed. Its apparent chaos was only the surface of an underlying unity. That unity became the foundation of modern physics. Without Maxwell, there could be no Einstein, no relativity, no quantum mechanics. His equations introduced the concept of the field as a real entity, something that existed everywhere, carrying energy and information. They taught humanity that what we call empty space is not truly empty but filled with potential, with the capacity to vibrate and transmit light itself. His journey was not easy. Maxwell's health was fragile, and his time was short. Yet his work was driven by something beyond ambition, a deep spiritual and intellectual curiosity about the harmony of nature. He saw the universe not as a cold mechanism, but as a divine symphony governed by order and logic. His unification of electricity and magnetism was an act of faith in that order, a belief that behind the apparent complexity of the world, there existed a single, elegant truth. The brilliance of Maxwell's mind lay not only in what he discovered, but in how he thought. He could move seamlessly between the physical and the mathematical, between intuition and proof. When he introduced the concept of electromagnetic waves, he was not simply solving equations. He was revealing a cosmic dance, an interplay of energies that would explain the light of the stars and the transmission of human voices across oceans. His vision transcended the laboratory, it touched the very structure of reality. By the end of the 1860s, Maxwell's unification stood complete, though few fully understood it. The four equations that bore his name would become the cornerstone of modern physics, guiding future generations toward relativity and beyond. But in Maxwell's own time, his achievement remained underappreciated, a masterpiece ahead of its audience. Only later, when Heinrich Hertz experimentally confirmed the existence of electromagnetic waves, would the world recognize that Maxwell's imagination had reached further than any experiment could in his lifetime. For now, in the mid-19th century, his vision stood as a lighthouse in the fog, a promise that the universe was not divided into separate realms of electricity, magnetism, and light, but unified under one grand theory. And through that vision, Maxwell had done more than explain nature, he had given humanity a new way to perceive it. As Maxwell's thoughts deepened, he began to sense that nature's hidden rhythm was not random, but woven through patterns of balance. He could almost feel that wherever electricity moved, magnetism followed like a shadow. Wherever magnetism danced, electricity whispered in return. It was a duet that no one had yet written down as music, and Maxwell was determined to compose it. The more he read Faraday's notes, the sketches of field lines curling through space, the more he saw a living geometry beneath them. To most scientists of his day, those drawings were only suggestive pictures. To Maxwell, They were evidence that invisible energy had structure, that space itself could carry tension and motion. He spent nights translating those pictures into mathematics, inventing symbols and relationships that could speak what Faraday had only shown with lines. It was not easy work. Sometimes he would spend weeks trapped between intuition and algebra, trying to find the single form that could express both the electric and magnetic laws without contradiction. He imagined space filled with an unseen medium, an ether, vibrating with stored energy. Through that invisible sea, electric and magnetic influences traveled, pushing and pulling each other in harmony. Whether the ether was real or not hardly mattered. What mattered was the logic it revealed. He began to describe curls and divergences, showing that when an electric field changes, a magnetic field springs up, and when a magnetic field changes, an electric field emerges in reply. This was the seed of unification, that the two forces were not separate, not even sequential, but manifestations of the same underlying phenomenon. Maxwell's equations, though still forming, hinted at something astonishing: the possibility that self-sustaining waves could propagate through emptiness, with each field regenerating the other as they advanced. He could almost see them racing through the void, carrying both energy and information. It was a thought so daring that many of his contemporaries refused to follow it. They believed in static charges and iron filings, not in abstract waves traveling through nothing. Yet Maxwell's quiet confidence never broke. He saw beauty where others saw confusion. In his lectures at Cambridge, he spoke with a soft Scottish accent, often shy, but when he described fields and forces, his eyes lit with excitement. Students would recall how he drew loops and arrows on the blackboard, tracing the flow of invisible energy as if painting an unseen universe. Imagine, he would say, that every point in space has a direction and magnitude, a vector, that tells you what the electric and magnetic forces are doing there. To the young minds listening, it felt like revelation. Suddenly, the world was not made of isolated objects, but of continuous patterns binding them together. Maxwell's mathematics turned this vision into a language that anyone with courage could read. His work built bridges across centuries of thought. Coulomb's law, which described the pull between charges, and Ampere's law, which defined how currents create magnetism, were pillars standing apart. Maxwell connected them with new links, introducing terms that accounted for displacement currents and the dynamic interaction between time-varying fields. In that single move, he transformed static electricity and magnetism into a single theory of electromagnetism. What had once been two disconnected sciences became one continuous framework. It was as if he had taken two separate melodies and woven them into a symphony, each theme enhancing the other until the harmony was undeniable. Outside the university, technology was entering an age of wonder. Telegraph lines stitched continents together, carrying signals of human thought across distances unimaginable a century earlier. Yet no one truly knew why the pulses moved, why the magnetic needle twitched, why sparks leapt through the air. Engineers worked by rule and by habit, but not by fundamental understanding. Maxwell's equations were about to provide that missing foundation. They explained the invisible architecture underlying every telegraph wire, every spark of lightning, every glow of an aurora. Through his mathematics, humanity gained not only knowledge but control, the ability to predict and eventually harness the electromagnetic forces that animate the modern world. Maxwell often retreated to his family estate, Glenlair, to think in solitude. There, amid the rolling green hills of Scotland, he found the clarity that busy laboratories could not offer. He would pace the grounds with a notebook in hand, sketching diagrams of rotating vortices and lines of force winding through space. Sometimes he read poetry, drawing inspiration from rhythm and metaphor. Other times he played the guitar softly in the evenings, letting music guide his intuition. For him, physics was not cold calculation. It was art written in the language of logic. To unite electricity and magnetism was not merely to solve a problem, but to reveal a deeper aesthetic unity in nature. As his ideas matured, The scientific community began to sense that something profound was taking shape. Maxwell's papers appeared dense, filled with vector calculus that many physicists found alien. But those who looked deeper realized that his equations carried a promise. They predicted not only known phenomena but new ones yet unseen. One of these was the electromagnetic wave. If a changing electric field could create a magnetic field, and that magnetic field could in turn create a new electric field, the two could sustain a ripple moving through empty space. When Maxwell calculated the speed of that wave, he was stunned. It matched the measured speed of light. In that instant, electricity, magnetism, and optics became one. That revelation marked the climax of his vision. For centuries, light had been treated as a separate mystery, sometimes imagined as particles, sometimes as waves in a special medium. Now, Maxwell had shown that light itself was an electromagnetic phenomenon, the visible part of a vast spectrum of radiation. He had built not just a bridge, but an entire continent of understanding connecting electricity, magnetism, and light. The chaotic diversity of forces that once bewildered scientists now fit within 4 elegant equations. To the modern eye they appear simple, almost inevitable, but in Maxwell's time they were revolutionary. Mathematical poetry carved into the heart of nature. Maxwell's unification became a mirror for human thought. It showed that truth often hides in the relationships between things rather than in the things themselves. Where previous generations saw separation, he saw continuity. Where others saw complexity, he saw pattern. His achievement encouraged later thinkers to search for unity elsewhere, in atoms, in forces, even in space and time themselves. It prepared the stage for Einstein, who would later find in Maxwell's constant speed of light the key to relativity, and for the quantum pioneers who would discover that energy, too, comes in interwoven fields. By the time Maxwell passed away in 1879, at only 48, the full impact of his work was not yet recognized. Many still treated his theory as a mathematical curiosity, too abstract for practical use. Yet within a few decades, Hertz would detect electromagnetic waves exactly as Maxwell had predicted, and Marconi would send the first wireless signals across the sea. Each discovery was a living echo of Maxwell's vision. A vision born not from laboratory spectacle, but from patient reasoning and profound imagination. In retrospect, Maxwell's quest to unite electricity and magnetism was more than a scientific breakthrough, it was a philosophical shift. It changed how humanity perceives the universe, not as a collection of isolated parts, but as a continuum of interactions. Every flicker of light, every signal sent, every magnetic compass turning north, is a small demonstration of the harmony he revealed. His equations whisper that the cosmos is coherent, that the same laws that stir electrons in a wire also govern the shimmer of distant stars. Today, we measure his influence in the quiet hum of electric motors, the glow of screens, the vast networks of communication encircling the planet. Yet beneath all that technology lies the same dream Maxwell once pursued in the solitude of Glenlair, to find unity in diversity, to write the hidden music of nature into human understanding. His legacy endures not merely in textbooks, but in the pulse of every photon that crosses the universe. He had seen, long before others, that electricity and magnetism were 2 expressions of a single cosmic breath, and by giving that breath a voice in mathematics, he helped humanity hear the song of the universe itself. The mid-19th century was an age of wonder and confusion in equal measure. The Industrial Revolution had filled the world with the hum of machines, the crackle of telegraph lines, and the glow of electric sparks. Yet the very forces driving these marvels were still shrouded in mystery. Electricity could light cities, magnetism could guide ships, and lightning could tear through the sky. But no one truly knew why these forces behaved as they did. It was as if humanity had learned to ride the waves of an invisible ocean, without ever knowing the ocean's shape. And into that restless sea of questions stepped James Clerk Maxwell, armed with nothing but paper, ink, and the infinite patience of a man who believed that mathematics could reveal the mind of nature itself. Maxwell's journey toward the formulation of his four equations was not a single moment of genius, but a long, deliberate ascent up a mountain of ideas built by those before him. He looked to Michael Faraday's experiments with reverence, seeing in Faraday's field lines something deeper than metaphor. While Faraday had sketched invisible curves to represent magnetic forces, Maxwell saw within them a geometry of reality, a structure that could be expressed not through art, but through mathematics. He began translating those lines into equations, symbols, and relationships. He wanted to describe not just the results of forces, but their origins and their eternal dance. Each of Maxwell's equations began as a seed planted in centuries of exploration. Coulomb's work had described how electric charges attract and repel each other through an inverse square law. Gauss, with his profound intuition, had shown that the total electric flux through a closed surface depended only on the total charge enclosed within. Ampère had explored how electric currents create magnetic fields, while Faraday had discovered how changing magnetic fields could induce electric currents. The problem was not that physics lacked data, it lacked unification. Each law described a piece of the puzzle, yet none connected to form the full picture. Maxwell's task, then, was not to create from nothing, but to unify everything. He did not treat the discoveries of others as isolated monuments, but as fragments of a deeper harmony. He saw what others had missed. These forces were not just related, they were inseparable. The electric and the magnetic were not two forces at all, but two aspects of a single dynamic field. Like the crest and trough of a wave, one could not exist without the other. To express this unity, Maxwell turned to the language of calculus, the mathematics of change and continuity. He began developing equations that could describe how electric and magnetic fields evolve in both space and time. He defined how electric charges create electric fields, how magnetic poles create magnetic fields, how changes in these fields influence each other, and how both can move as waves through empty space. He envisioned the universe filled with invisible vectors, each representing a force's direction and magnitude, weaving a tapestry of interaction too fine for the eye to see but perfect for the mind to calculate. The first of his great equations emerged as a formal expression of Gauss's law. The total electric flux through any surface equals the charge enclosed divided by a constant. This simple statement encoded the very nature of electric charge, that it is the source of electric fields. The second equation followed naturally, showing that magnetic monopoles do not exist. Magnetic field lines always form closed loops, meaning there are no isolated north or south poles. Together, these two laws describe the static world, the stillness of charge and magnetism at rest. But nature is never still, and Maxwell knew that to understand its essence, one must describe motion, transformation, and flow. That led him to the third equation, drawn from Faraday's law of induction. Faraday had shown that a changing magnetic field can induce an electric field, something that could power motion, light, and energy. Maxwell expressed this insight mathematically, showing that the curl of an electric field equals the negative rate of change of a magnetic field. It was elegant, but something was missing, a balance to complete the symmetry. When Maxwell examined Ampere's law, which described how currents create magnetic fields, he realized a flaw. If electricity could generate magnetism, then the reverse should also be true. Changing electric fields should generate magnetic fields, even when no current is flowing. This was the breakthrough. Maxwell introduced a new concept he called displacement current, a term not tied to the motion of electrons, but to the variation of the electric field itself. It was his bridge between the static and the dynamic, the missing piece that made the equations consistent and complete. With that one insight, the puzzle finally assembled into a whole. The result was a set of 4 differential equations that could describe every behavior of electromagnetic fields, from the smallest laboratory experiment to the boundless expanse of the cosmos. Yet even Maxwell could not have fully predicted the beauty that his own mathematics revealed. When he combined his equations, Eliminating variables to find their consequences, something astonishing appeared. They predicted that electromagnetic disturbances would travel through space in waves, and the calculated speed of those waves matched exactly the speed of light measured by physicists. Light itself, he realized, was an electromagnetic phenomenon. It was the ultimate connection, the moment when electricity, magnetism, and optics became one. Maxwell wrote of this revelation with a calm humility that belied its magnitude. He said, "We can scarcely avoid the conclusion that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena." To him, this was not just mathematics, it was a glimpse of unity in the universe. He had shown that the light from the sun, the spark in a wire, and the invisible radio waves that would one day circle the Earth were all governed by the same elegant framework. 4 equations, compact, silent, and universal, described everything. In the quiet of his study at Glenlair, Maxwell would often work deep into the night, ink staining his fingers, his desk covered in notes filled with integrals and vector symbols. His wife, Catherine, would sometimes bring him tea and watch as he muttered equations under his breath, lost in thought. It was in these long hours that the 4 equations matured from scattered insights into a complete theory. He knew their power, but perhaps not their destiny, that they would become the foundation of modern physics, the backbone of electromagnetism, and a guiding light for generations to come. At the time, few understood the depth of what he had accomplished. Many physicists still clung to mechanical models of the ether, struggling to visualize fields as real entities. They imagined invisible gears, fluids, or spinning vortices filling space, carrying the energy of waves. Maxwell himself often used such imagery as a tool of thought, not as literal truth. His genius lay in recognizing that the equations were more real than any imagined mechanism. They were the laws of nature in their purest mathematical form. His formulation represented a turning point in science. Before Maxwell, physics was largely empirical, based on observation and experiment. After Maxwell, it became predictive, capable of describing phenomena unseen and untested. His equations foretold the existence of electromagnetic waves decades before anyone could detect them. When Heinrich Hertz finally confirmed their existence in the 1880s, the scientific world stood in awe. The invisible ocean Maxwell had described became tangible. Radio, radar, and the entire age of wireless communication were born from that confirmation. Maxwell's 4 equations were more than a scientific triumph, they were a philosophical one. They embodied the principle of unity, that diverse forces, seemingly distinct, could be woven into one consistent theory. They showed that nature's laws are not arbitrary, but interconnected, that beauty and truth often meet in the symmetry of mathematics. It was as if the universe had been speaking all along in a language humanity was only just learning to hear, and Maxwell had given it a voice. Today, the equations appear on classroom walls, carved into memorials, and printed in every physics textbook. But behind those symbols lies a story of human imagination, persistence, and wonder. Maxwell did not simply calculate. He listened to Faraday's intuition, to nature's silence, to the logic of the unseen. And through that listening, he wrote the 4 verses of a cosmic song, one that continues to echo through every scientific discovery since. Even Einstein, decades later, would bow before Maxwell's creation. The work of Maxwell, he said, changed the world forever. It was these equations that inspired him to question the nature of light's speed, to develop relativity, to show that space and time themselves must bend to preserve Maxwell's constant. In this sense, Maxwell did not just formulate equations. He formulated the future of physics. By the end of his life, Maxwell's health began to fail, but his ideas had already begun their infinite journey. In the flicker of every light bulb, the hum of every transformer, the signal of every antenna, his equations live on. They continue to shape the modern world, from the design of electronics to the exploration of distant galaxies. His 4 laws became the grammar of the electromagnetic universe, guiding humanity from the age of static sparks to the era of cosmic understanding. He had done more than describe a set of rules, he had captured the unity of existence. Where others saw chaos, Maxwell found order. Where others saw separation, he found connection. His four equations, compact yet boundless, remain among the most beautiful creations of the human mind. A timeless bridge between the seen and the unseen, between the physical and the mathematical, between the curiosity of man and the harmony of the cosmos. When Maxwell finally gathered the strands of thought that would become his four great equations, he knew he was holding something extraordinary, though the magnitude of it was still difficult even for him to grasp. The pages on his desk at Glenlair were filled with symbols and loops of ink, can E, tout E, B die B. To anyone else they would have seemed like meaningless hieroglyphs, but to Maxwell they were living expressions, breathing with the rhythm of the universe. Each symbol was a pulse, each derivative a motion, each constant a heartbeat of nature. He would read them aloud to himself softly, almost like poetry. The first said that electric charges create electric fields. The second said that magnetic poles cannot exist alone. The third revealed that a changing magnetic field gives rise to an electric field. And the fourth completed the circle, showing that magnetic fields are generated both by electric currents and by changing electric fields. 4 lines, infinite meaning. He had taken centuries of experiment and woven them into a single fabric. Yet his accomplishment was not simply to write equations. It was to end a long philosophical war within physics. For generations, thinkers had debated whether forces acted instantaneously across empty space, or whether they were carried by something real that filled that space. Maxwell's equations answered without words. Space itself was active. It could store energy, transmit vibrations, and guide motion. The old image of distant objects tugging at one another through nothingness dissolved. In its place arose a new concept, the field. That single word, field, transformed science forever. It meant that every point in the universe had a measurable condition, an electric intensity, a magnetic twist, even if no matter was present. Fields were not material in the ordinary sense, but they were physical. They carried energy, momentum, and information. They could propagate as waves, bend around obstacles, and interfere with one another. They were the medium of reality itself. Maxwell's equations were the grammar by which those fields spoke. In Cambridge and London, Maxwell's colleagues struggled to follow his logic. The mathematics was dense, the physical picture was abstract. Some dismissed his theory as a brilliant but unnecessary complication. Others sensed that it held something profound yet could not articulate why. Maxwell himself was patient. He understood that great shifts in understanding take time. The true logic of this world, he once wrote, is in the calculus of probabilities. He knew that certainty comes only after evidence, and evidence would come soon enough. His papers from the 1860s circulated quietly through scientific journals, but they were slow to ignite. The elder generation of physicists still thought in terms of wires, batteries, and magnets, solid things they could hold and see. Maxwell asked them to imagine invisible loops of energy flowing through empty air, fields stretching infinitely through space. It was too radical for most, and yet in those same years, the telegraph wires stretching across continents were already carrying proof that his theory described reality more accurately than anyone guessed. Every flicker of current in those cables set up electromagnetic waves that pulsed outward through the atmosphere, invisible messengers obeying Maxwell's mathematics. In the decades that followed, a new generation would take up his challenge. Among them was Heinrich Hertz, who built delicate apparatus in a dim laboratory to detect the electromagnetic waves Maxwell had predicted. When Hertz saw sparks jump across a tiny gap in synchrony with another set of sparks across the room, he realized that the waves were real. Space was vibrating exactly as Maxwell had said it would. From that moment, the four equations were no longer just theory. They were the heartbeat of the universe made visible. The discovery opened doors humanity had never imagined. Guglielmo Marconi turned those same waves into the first wireless telegraph. Later, engineers would transform them into radio, radar, television, and every form of wireless communication. Astronomers would tune antennas to hear the whisper of cosmic radiation left over from the birth of the universe. Everywhere, from the smallest transistor to the vastness of interstellar space, Maxwell's equations ruled. And yet, their meaning went beyond technology. They changed how physicists thought about nature. Before Maxwell, the universe was a collection of particles and forces acting through contact or distance. After Maxwell, it became a continuous entity, an ocean of fields where matter was merely a disturbance. His mathematics suggested that energy could move through space without the need for material support, that the void itself was capable of motion. The concept of emptiness was replaced by fullness. Even the vacuum became alive with potential. In that sense, Maxwell's work marked the birth of modern physics. It prepared the intellectual ground on which Einstein, Planck, and others would later build relativity and quantum mechanics. Einstein himself often said that Maxwell's equations were the most profound and fruitful physical laws ever discovered. When he sought to understand how light behaved for observers in motion, he began by assuming that Maxwell's equations must remain true for everyone. From that single assumption, relativity was born. But beyond the scientific revolution, there was something deeply human in Maxwell's story. He was a man driven not by ambition, but by curiosity, by the quiet conviction that beauty and truth are one. His notebooks reveal a constant dialogue between logic and imagination. He would pause amid pages of mathematics to jot down a line of poetry or a playful sketch. Friends remembered him as gentle, humorous, and humble. When asked about the meaning of his discoveries, he would often deflect with a smile, suggesting that he had only rearranged the ideas that nature had placed before him. Still, one cannot read his equations without feeling the pulse of genius. They are astonishingly compact, as if the universe conspired to express its workings in the simplest possible form. Written with modern symbols, they fit neatly on a single line each, and yet those few lines describe phenomena ranging from the glow of a candle to the signals exchanged between planets. They govern the behavior of electric circuits, the operation of MRI scanners, the path of radio waves, and the fusion of stars. Every photon, every spark, every flash of lightning moves according to their command. It is tempting to imagine the moment when Maxwell realized that light was an electromagnetic wave. Perhaps it was late at night, rain tapping the window panes of Glenlair, the fire burning low. He would have been bent over his desk, surrounded by equations and the soft murmur of thought. Then the numbers would have aligned. The speed of the predicted wave matched the measured speed of light. It must have felt like hearing the universe breathe. For a moment, the barrier between the known and the unknown dissolved. He had discovered that illumination itself, literal and metaphorical, was a vibration of the same forces that powered the telegraph and the magnet. The news spread slowly, but its echo was infinite. Scientists began to see that light was only one small part of a much broader spectrum. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, all manifestations of Maxwell's unified field. The electromagnetic spectrum became a new map of reality, stretching from the tiniest oscillations to the most energetic cosmic rays. Humanity had gained a new sense of vision, able to see beyond the visible into the hidden structure of the cosmos. As the 19th century turned to the 20th, the full consequence of Maxwell's work began to bloom. Engineers developed alternating current systems that transmitted power across cities. Inventors built devices to generate and receive electromagnetic signals. Astronomers used radio telescopes to explore the universe. Every advancement traced its lineage back to those four lines of mathematics. Even in modern particle physics and cosmology, Maxwell's equations remain embedded, their form echoed in the equations that describe nuclear and quantum fields. They are the template of unification, the model of how separate phenomena can emerge from one fundamental law. In quieter moments, one might wonder what Maxwell himself would think if he could see how far his vision had reached. Perhaps he would smile at the satellites orbiting Earth, each whispering signals through the electromagnetic sea he once imagined. Perhaps he would marvel at how his equations guide probes to the edges of the solar system, translating mathematical fields into trajectories and communications across billions of kilometers. He might even feel a quiet satisfaction knowing that the light from distant galaxies, traveling for aeons, obeys the same rules he wrote in his study. But Maxwell would likely say that the beauty of science lies not in conquest, but in comprehension. His equations are not chains binding the universe, but windows opening into its harmony. They remind us that the cosmos is intelligible, that the same simplicity governing the spark in a lab also governs the light of the stars. In their symmetry, one can almost sense a moral lesson. Unity exists beneath diversity, order beneath apparent chaos. In the end, the formulation of Maxwell's 4 equations was more than a milestone. It was a revelation that the world is woven from fields, vibrations, and interconnections. From them came not only modern technology, but also a new philosophy of nature. They invite us to see the universe not as a collection of separate parts, but as an intricate symphony, every note resonating with every other. The whisper of a radio signal, the warmth of sunlight, the pulse of a distant quasar, all sing the same song in different keys. That is why, more than a century later, Maxwell's work still feels alive. Each time a physicist writes tau e tamau a by bait or e tarapayo, they are participating in a conversation that began with one man's search for unity. Each calculation, each experiment, each signal crossing the sky is an echo of his discovery. The universe speaks through those equations still, telling us that chaos and cosmos are one and the same when seen through the right lens. And so, the story of Maxwell's equations is not merely the story of mathematics. It is the story of humanity learning to listen, to the quiet order behind the noise, to the symmetry beneath the storms, to the eternal dialogue between electricity and magnetism that gives birth to light itself. Through 4 simple laws, Maxwell gave the universe a voice, and in hearing it, we discovered our own. In the vast tapestry of scientific discovery, certain moments stand out, not just for what they reveal, but for the way they reshape our understanding of reality itself. The 4th keynote in Maxwell's Odyssey, the unification of light and electromagnetic waves, was one of those moments. It was not born in a laboratory full of humming machines or in the spark of visible experiments, but in the quiet, contemplative space of a brilliant mind imagining the invisible. James Clerk Maxwell, having spent years translating Faraday's intuition into precise mathematics, began to sense a connection that no one had yet seen. That light, the very thing that illuminates our world, is itself an electromagnetic phenomenon. For centuries, light had been a source of mystery and debate. Philosophers and scientists argued over its nature. Was it a particle, traveling in straight lines like tiny corpuscles? Was it a wave, rippling through some unseen ether? Newton-Huygens and countless others had probed its secrets, producing elegant experiments, but leaving the fundamental question unresolved. Then came Maxwell, bridging the gap between what could be observed and what could be calculated. He did not merely examine light as an optical phenomenon. He approached it as a fundamental force, inseparable from electricity and magnetism. The revelation came from his equations themselves. When he combined his 4 equations, introducing the concept of the displacement current, he noticed a remarkable consequence. Disturbances in the electric and magnetic fields could propagate through space, sustaining one another. And when he calculated the speed of these disturbances, he found it matched the known speed of light, measured with exquisite precision by astronomers and physicists of his era. Light was no longer an isolated mystery. It was a wave of the very fields Maxwell had described, a ripple in the unified fabric of the electromagnetic universe. This realization was profound not only scientifically but philosophically. It suggested that the forces acting in the laboratory, the sparks and magnets observed daily, were connected to the cosmic phenomena of sunlight and starlight. Maxwell's mathematics provided a bridge between the finite and the infinite, between human perception and the distant reaches of the universe. The invisible waves of electricity and magnetism, which could now be seen as the origin of light itself, were the threads that tied together the microcosm of wires and circuits with the macrocosm of planets, stars, and galaxies. At the time, such ideas were nearly unimaginable. Physicists of the 19th century were accustomed to forces acting through matter or through some hypothesized ether, a medium whose existence could not be directly observed. Maxwell's insight removed the need for mechanical speculation. Instead, he showed that the fields themselves were real and sufficient. The space through which light traveled was not empty, it was alive with potential, capable of carrying the vibrations that make vision, warmth, and energy possible. The universe, once seen as a stage of disconnected events, became a continuous, dynamic web. Maxwell's unification also set the stage for the technologies that define the modern age. Once it was understood that light was an electromagnetic wave, it became conceivable to generate and detect other wavelengths beyond human vision. Hertz's experiments would later confirm the existence of radio waves, and Marconi's wireless telegraphy would exploit them to connect continents. The realization that light is a wave in an electromagnetic field opened the door to radio, television, radar, and the entire spectrum of communications technology. Every visible and invisible signal traversing space does so because Maxwell first imagined the deep connection between electric and magnetic forces and the waves they sustain. The elegance of this unification lies not only in its predictive power but in its simplicity. 4 equations, when combined, explain a vast range of phenomena: the reflection and refraction of light, the behavior of antennas, the propagation of radio waves, and the cosmic glow of stars billions of light-years away. Maxwell's insight transformed the way humans perceive both the visible and the invisible, revealing that nature's diversity arises from a single underlying structure. What was once a confusing collection of experiments and observations now appeared as a coherent, interwoven whole. Beyond practical implications, the unification of light with electromagnetism carried a profound philosophical lesson. It illustrated that seemingly disparate phenomena are often manifestations of a deeper, elegant order. The lightning bolt in the sky, the spark in a laboratory, the gentle glow of a candle, and the rays of the sun all obey the same fundamental principles. The universe, in its complexity, exhibits unity, a harmony that Maxwell captured in equations of unparalleled clarity. This realization inspired later generations of physicists, including Einstein, who would build upon Maxwell's framework to uncover relativity and further explore the fundamental symmetries of nature. Maxwell's discovery was also a testament to the power of imagination guided by rigorous thought. He did not see light with his eyes alone. He visualized it mathematically, imagined its vibrations, and connected it to the invisible forces surrounding him. He bridged intuition and formalism, experiment and theory, in a way that few minds can achieve. His equations became more than symbols. They became a language for describing reality itself, a code revealing the hidden structures of the universe. Today, every photon reaching Earth carries the legacy of Maxwell's insight. Every radio transmission, every microwave, every X-ray, and every visible beam of light is an echo of that unification. His work reminds us that human understanding often begins not with observation alone, but with the courage to imagine the connections others have overlooked. By uniting light with electromagnetic waves, Maxwell not only solved a scientific puzzle, but also illuminated the profound coherence underlying the cosmos, offering a vision of the universe that continues to inspire awe and discovery. In the end, the 4th keynote is more than a scientific milestone. It is a revelation of perspective. It teaches that forces once thought separate are intertwined, that the visible world is part of a vast continuum of energy, and that understanding comes from seeing connections invisible to the eye but clear to the mind. Through Maxwell's vision, the universe became a symphony, with light as its melody and electromagnetic fields as its harmony. humanity's ability to perceive, manipulate, and communicate across space rests upon this fundamental unification, a legacy that continues to shape both our technology and our understanding of the cosmos. The story of Maxwell's genius does not end with the unification of light and electromagnetism. The fifth keynote, the profound realization of the predictive power of his equations, reveals how a single set of mathematical statements could reach far beyond observation, forecasting phenomena that humanity had not yet discovered. Maxwell's equations were not mere tools to describe known forces, they were a window into the unseen, a map of possibilities hidden within the very fabric of reality. In that sense, he transformed science from a record of what is observed into a compass pointing toward what could be discovered. Before Maxwell, physics was largely retrospective. Scientists cataloged observations and devised laws to fit the data, but they rarely ventured into realms untested by experiment. Faraday had discovered induction, Coulomb had measured charges, Ampère had traced currents, yet all these laws were confined to what could be seen or directly measured. Maxwell dared to go further. He asked not only, "What do we know?" but, "What must be true?" Even if we cannot yet detect it. His equations implied a universe brimming with possibilities, waves and disturbances traveling through space, energies vibrating silently until technology could reveal them. The predictive power of his work became evident as the century unfolded. When Heinrich Hertz performed experiments in the 1880s, generating electromagnetic waves in the laboratory, he was testing ideas that Maxwell had formulated decades earlier. Hertz did not discover a new law, he confirmed a truth Maxwell had already written in the language of mathematics. These waves, invisible yet real, propagated precisely as Maxwell had predicted. It was one of the first times in history that a theoretical framework led the way, directing experimental discovery rather than merely explaining it afterward. This predictive aspect of Maxwell's equations revolutionized the relationship between theory and experiment. They showed that the mind, guided by mathematics and imagination, could reach into the invisible realms of nature and emerge with insights confirmed by reality. Maxwell's equations were not limited to the laboratory. They described phenomena across scales, from the flicker of sparks in a wire to the vast radiance of stars. Every photon, every radio wave, every pulse of electromagnetic energy obeyed the rules he had laid down. In this, his work foreshadowed the modern view that the universe is comprehensible through fundamental principles, waiting for the human mind to decode them. One of the most striking consequences of Maxwell's predictive genius was the recognition of the electromagnetic spectrum. Light was only a small portion of the waves his equations described. Beyond the visible lay infrared, ultraviolet, radio, X-rays, and gamma rays, each obeying the same laws, each a silent messenger traveling through the cosmos. The idea that humanity could one day harness these invisible energies seemed fantastical in Maxwell's time, yet his equations guaranteed their existence. This was a profound expansion of the imagination, revealing realms of energy and communication that would later define technology, medicine, and astronomy. Maxwell's foresight also reshaped the philosophy of science. He demonstrated that the universe operates according to coherent principles, that its behavior is not arbitrary, and that the hidden mechanisms governing matter and energy can be uncovered through careful reasoning. His equations embody the conviction that nature is intelligible, that curiosity guided by logic can reveal truths beyond immediate perception. For generations, scientists would follow this approach, using mathematics to predict phenomena before instruments could detect them. Whether it was radio waves, subatomic particles, or the gravitational waves Einstein's equations would later predict. Even more profoundly, Maxwell's predictive insight altered humanity's view of light and communication. The realization that electromagnetic waves could travel through space without a material medium suggested a new kind of connection between distant points. Long before radio towers and satellites, Maxwell's equations implied that energy and information could traverse vast distances with perfect fidelity. following the silent rules of the cosmos. This principle would eventually lead to wireless communication, radar, and the global exchange of knowledge, all born from the predictive clarity of his work. At a more philosophical level, the predictive power of Maxwell's equations embodies a human aspiration, the desire to see beyond the immediate, to reach into the invisible, and to trust that patterns exist even when they are not apparent. Maxwell trusted that nature had an underlying order, and his faith in that order allowed him to write equations that described the unseen. In doing so, he transformed scientific inquiry from a reactive practice into a proactive exploration, proving that understanding could precede observation and that imagination, guided by reason, could illuminate hidden truths. Maxwell himself was often reflective about the implications of his work. He understood that while experiments confirm theories, the equations themselves are a form of discovery. They contain within them possibilities that may remain invisible for decades, waiting for human ingenuity to realize them. In this sense, the fifth keynote is both a celebration of human intellect and a testament to the deep coherence of the natural world. Maxwell's equations are not just descriptive, they are predictive, opening doors to phenomena humanity has yet to encounter, revealing that the universe is more interconnected and comprehensible than it often appears. Ultimately, this keynote highlights the essence of scientific vision. It reminds us that the role of theory is not simply to catalog what is seen, but to reveal what must exist. Maxwell's predictive power transformed physics into a forward-looking endeavor, where mathematics becomes a tool to uncover hidden truths, and imagination guided by logic becomes a lens to perceive the universe in its fullest extent. The consequences of this approach ripple through every aspect of modern science, from telecommunications to astrophysics, from medical imaging to space exploration, illustrating that insight can transcend the limits of observation and reshape the way humanity engages with reality. In the story of Maxwell, the fifth keynote stands as a beacon of intellectual courage and vision. It celebrates the ability of a single mind to peer into the invisible, to predict the existence of waves, energies, and connections far beyond what was measurable in his lifetime. It is a reminder that discovery is not always immediate, that the laws of nature often whisper before they shout, and that the clarity of thought, expressed through mathematics, can illuminate the hidden architecture of the universe. Maxwell's predictive genius remains a cornerstone of modern science, inspiring generations to seek not only what is seen but also what can be imagined, calculated, and ultimately revealed. Maxwell's journey, the profound implications of his equations for modern technology and communication, reveals how abstract thought can ripple through society, reshaping the very fabric of daily life. Maxwell, in his quiet study at Glenlair, could scarcely have imagined the technological revolutions his mathematics would unleash. His work described a universe governed by electric and magnetic fields, vibrating in harmony, carrying energy across empty space. At the time, these were elegant abstractions, lines and symbols on paper. Yet within them lay the blueprint for the wireless world, for the transmission of information at speeds once thought impossible, and for an era in which humans would extend their reach across continents and, eventually, into space itself. Maxwell's equations describe a reality that transcends the laboratory. They dictate how electric charges move, how currents generate magnetic fields, and how changes in one field create disturbances in the other. Each of these principles, abstract and theoretical in his time, became the foundation of technologies that now define modern civilization. The telegraph, which already connected distant cities, was just the beginning. Once the equations revealed that electromagnetic waves could travel through space without a physical medium, inventors began to see the possibility of wireless communication. Hertz's laboratory sparks, initially a confirmation of theory, became the first whisper of signals that could traverse the globe. It is striking to consider that every wireless transmission, every radio broadcast, every television signal, every cellular phone conversation, obeys the very rules Maxwell formulated. The invisible waves carrying voices and images through the air are manifestations of the mathematical relationships he wrote more than a century earlier. The hum of electricity, the flicker of lights, and the signals passing through fiber optics are all expressions of principles that were, in Maxwell's time, entirely theoretical. His equations provided not just understanding, but the predictive certainty necessary to transform theory into invention. The predictive power of these equations meant that engineers could design devices with confidence, knowing that the abstract mathematics described reality. Radio transmitters could be tuned to precise frequencies, antennas shaped to optimize reception, and circuits built to harness energy efficiently. Maxwell's insight, that changing electric fields generate magnetic fields and vice versa, became the operational principle behind every wireless system. Without this understanding, modern communication would be impossible. Every cell tower, satellite link, and Wi-Fi network traces its origin to the subtle curls and divergences that Maxwell first wrote on his study desk. Beyond communication, Maxwell's work laid the groundwork for countless other technological breakthroughs. Electromagnetic theory governs electric motors and generators, which power industry and homes alike. MRI machines essential to modern medicine rely on precise manipulations of magnetic fields predicted by Maxwell. Radar, crucial in aviation, meteorology, and defense, uses controlled electromagnetic waves to detect objects at great distances. Even the light that illuminates cities and devices, from LEDs to lasers, is guided by principles first unified in his equations. The impact of Maxwell's mathematics is not confined to the laboratory or the classroom, it is woven into the everyday experience of billions of people worldwide. What makes this keynote particularly profound is the interplay between theory and invention. Maxwell did not construct antennas or radio transmitters, yet his work made these devices possible. It demonstrates a timeless truth about science. The act of understanding can precede practical application, and knowledge created in pursuit of curiosity can eventually transform society in ways the originator could scarcely imagine. Maxwell's equations are not static formulas, they are dynamic instructions embedded in nature, waiting for human ingenuity to bring them to life. Equally remarkable is the universality of Maxwell's equations. They apply equally to the smallest laboratory experiment and the vastness of space. Satellites orbiting Earth, communicating across thousands of kilometers, obey the same rules as a spark in Maxwell's laboratory. Radio astronomers, listening to signals from distant pulsars, interpret electromagnetic waves traveling across light years through space. The technology that shapes daily life, the communication that binds societies, and the instruments that explore the cosmos, all of these depend on the universality embedded in Maxwell's vision. Maxwell's insights also reveal a subtle philosophical message about the unity of knowledge. The same laws that govern electric and magnetic fields in a copper wire also govern the light of distant stars and the invisible radiation filling interstellar space. The microcosm and macrocosm are not separate, they are governed by the same principles. This realization underscores the interconnectedness of nature and human understanding. Every technological application, from the simplest flashlight to the most sophisticated space probe, is a small manifestation of the same cosmic order Maxwell revealed in his mathematics. In considering the sixth keynote, it is impossible to separate scientific insight from human impact. Maxwell's abstract equations became the engine for an era of rapid technological progress, accelerating global communication, expanding knowledge, and creating entirely new industries. The world we inhabit today, interconnected, illuminated, and wireless, is a direct consequence of his vision. Yet his work was never intended as a recipe for invention, it was an exploration of truth, a meditation on the unity of natural forces. And in that exploration, Maxwell provided the roadmap that humanity would follow to turn understanding into practical marvels. Finally, this keynote emphasizes the enduring lesson of Maxwell's legacy: the power of ideas transcends immediate utility. His equations were conceived in the quiet, reflective solitude of a 19th-century scholar, Yet their influence stretches into every corner of the modern world. From global communications networks to advanced medical imaging, from lighting cities to exploring distant galaxies, Maxwell's work is a testament to the enduring capacity of human intellect to perceive and harness the laws of nature. It is a reminder that the pursuit of understanding, driven by curiosity, rigor, and imagination, can yield transformations far beyond what the originator ever envisioned. In the end, the sixth keynote celebrates both the brilliance of Maxwell's mind and the vast consequences of theoretical insight. It reminds us that science is not merely a collection of facts, but a journey into understanding, and that the tools of mathematics and imagination can reshape the human experience. Maxwell's equations, abstract though they were, became the engine of modern technology, the foundation of communication, and the bridge between human ingenuity and the invisible forces of the universe. They show that one mind, guided by insight and curiosity, can illuminate not only nature but the very path of civilization itself. Maxwell's remarkable journey explores the enduring legacy of his work and its profound influence on both science and human thought. Beyond equations, experiments, and predictions, Maxwell's contributions transformed the way we perceive the universe and our place within it. His insights revealed a cosmos governed by harmony and interconnectedness, where forces once thought separate, electricity, magnetism, and light, are in fact facets of a single, elegant reality. This revelation reshaped the philosophical foundations of physics and set the stage for the scientific revolutions that would follow in the 20th century and beyond. Maxwell's equations did more than describe electromagnetic phenomena. They offered a new lens through which to understand nature itself. Before his work, scientists often approached phenomena as isolated occurrences, examining them one by one, as if the universe were a collection of disconnected puzzles. Maxwell's vision was different. He sought underlying unity, a framework that could link diverse phenomena through simple universal principles. In doing so, he demonstrated that nature's complexity emerges from fundamental simplicity, and that mathematics is not merely a tool for calculation, but a language capable of describing the structure of reality itself. This keynote also emphasizes Maxwell's role as a bridge between the experimental and theoretical traditions of science. He drew inspiration from Faraday's careful observations, translating intuitive field lines into precise equations. Yet he did not stop at describing known behavior. He predicted phenomena yet unseen, such as electromagnetic waves propagating through empty space. By doing so, Maxwell established the model for modern theoretical physics. Observation informs theory, but theory also predicts and guides future observation. This interplay between experiment and mathematics remains central to scientific inquiry to this day. Maxwell's legacy is evident not only in the laboratory but also in the cosmos. His equations govern the propagation of light across interstellar space, the behavior of magnetic fields in galaxies, and the dynamics of plasma in the Sun's atmosphere. The tools of modern astronomy, from radio telescopes to satellite observatories, rely on principles that he formalized. Every signal sent to distant planets, every measurement of cosmic radiation, and every observation of the electromagnetic spectrum across the universe is an application of his insight. In this sense, Maxwell's equations are as much a cosmic map as they are a laboratory tool. The philosophical implications of Maxwell's work extend to our understanding of the nature of reality. His equations suggest a universe that is coherent, interconnected, and intelligible. Forces that seem distinct in everyday experience are unified at a deeper level, revealing that underlying patterns govern all phenomena. This realization inspired subsequent generations of physicists to search for further unification. From Einstein's theory of relativity to the quest for a unified field theory combining electromagnetism, gravity, and quantum forces, Maxwell's legacy, therefore, is not confined to the 19th century. It echoes through every effort to uncover the fundamental laws of the universe. On a human level, Maxwell's work exemplifies the power of imagination guided by discipline. he demonstrated that abstract reasoning, when grounded in observation and mathematics, can reveal truths far beyond the reach of direct experience. His ability to see the invisible, to imagine the fields that fill empty space, and to express them with clarity and elegance, set a standard for intellectual creativity. Maxwell's life and work remind us that profound discovery often arises from curiosity, patience, and the willingness to explore ideas that initially seem intangible or impossible. Maxwell's influence also extends into technology and daily life. The devices that power the modern world, electric generators, motors, radios, televisions, cell phones, satellites, and medical imaging systems, operate according to principles he articulated. His equations transformed human capability, enabling instantaneous communication across vast distances and access to information once constrained by geography. The integration of theoretical insight and practical application that Maxwell embodied continues to shape innovation, illustrating the enduring relevance of fundamental science to societal progress. Furthermore, Maxwell's work serves as a reminder of the unity between simplicity and complexity. Four equations, elegantly formulated, govern phenomena that span scales from subatomic particles to galactic structures. In this, there is a lesson for both science and life, that apparent complexity often arises from underlying order, and that understanding can emerge when one seeks the connections, rather than merely cataloging isolated facts. Maxwell's genius lay not in discovering more data, but in revealing the relationships that bind phenomena together. The seventh keynote also underscores the inspirational power of Maxwell's vision. Scientists, engineers, and thinkers who followed in his footsteps often cited his work as a source of guidance and aspiration. Einstein, for instance, acknowledged Maxwell's equations as a foundation upon which he built the theory of special relativity. Hertz's experiments with electromagnetic waves confirmed the predictions Maxwell had made decades earlier. Innovators in telecommunications, medical technology, and space exploration continue to rely on the principles he articulated. Maxwell's influence, therefore, is both temporal and eternal, shaping discoveries long after his own life ended. Ultimately, the seventh keynote celebrates the enduring resonance of Maxwell's achievement. It is a testament to the power of human intellect to perceive the unseen, to unify disparate forces, and to transform abstract understanding into concrete progress. Maxwell's equations remain not only tools for scientists and engineers, but symbols of the potential for insight, creativity, and vision to illuminate the hidden architecture of the universe. They remind us that curiosity guided by reason can uncover truths that endure across centuries, shaping both our comprehension of nature and the trajectory of human civilization. In reflecting on this keynote, one sees that Maxwell's work transcends the boundaries of mathematics, physics, and technology. It represents a paradigm shift in how humanity conceives of the universe as an interconnected, intelligible whole, governed by elegant principles that link the visible and the invisible. The equations themselves, compact yet profound, encapsulate a worldview in which every spark, every wave, every ray of light, and every electromagnetic pulse obeys the same fundamental laws. Maxwell's vision thus continues to guide exploration, inspire innovation, and foster awe for the harmony that underlies all existence.